Yeah, so thank you very much. So I'll try to cover a second part of the meaning of this workshop, which is also addressed to fundamentals to technology. So I'm going to the more technological part, even if a lot of physics is involved in these developments. And of course, I would like to thank all the collaborators that contributed to this work. So the outline of the talk, first of all, I will just briefly discuss about spintec and the MRAM at spintec, the activities we have, the positioning of the MRAM in the memory hierarchy, few strategies for high-speed switching, a precessional STT-MRAM, use of a second-order anisotropy and perpendicular STT-MRAM to do fast switching, few things about high-speed SOT-MRAM, and if I have some time, maybe I will describe some of our recent developments for high-density MRAMs, and I will summarize. So, is it indeed in Grenoble? So, Spintec is a research lab which was created more than 15 years ago, so located in Grenoble area, having all these about 100 people working on Spintronics from very fundamental aspects to applied. So in terms of MRAM activity, of course, the activity in Spintec evolved from the initial configurations of the MRAM, which was initially field-based, either the cross-point, but also what we call the thermally assisted, or different flavors of what we call the spin transfer torque, up to what we called recently the spin orbit torque, or three-terminal device. So of course, from the beginning, the lab, which was funded also by some European projects here, was interested to develop concepts, but also to transfer technology to companies. And from the creation of the lab, there were some companies in the field of MRAMs and magnetic sensor that were created, like Crocus Technology, Evadris, H-Probe on instrumentation, or more recently, Antios on SOT. So of course, the basic cell of this MRAM is the magnetic tunnel junction, and the whole idea is how to handle the magnetization in this magnetic tunnel junction, either with a current, or as we saw in this workshop, eventually with the laser. So of course, all these type of architectures are addressing different markets in terms of microcontrollers, system on chip, up to the very dense DRAM, and depending on their properties, of course, the different flavors have different properties in terms of density, writing speed, endurance, or power. We can build what we call an application roadmap, depending on the technological node. So we can go to very low technological nodes down to the 10 nanometers described yesterday with different technologies. So today, I'm focusing more on what we call high-speed strategies, which are addressing these microcontrollers or cache applications. And if I have some time at the end, I will describe our recent developments in terms of high density. So, of course, there are some challenges for the high densities STT-MRAM applications, namely in terms of nano patterning. Of course, when we go to very dense pitch, depending on the etching strategy which is employed, there are some difficulties in closing too much the adjacent pillars due to the redeposition on side walls if an ion beam etching is used. Another thing is how we can guarantee, namely when we go to very small dimensions, the memory retention, which so far in the perpendicular STT is based on an interfacial anisotropy, which of course will not be enough to guarantee enough retention at this dimension. Also, what is interesting to mention, and it was also mentioned in some of the talks yesterday, is that typically that's the basic cell of the MRAM, which is a very simple magnetic tunnel junction. At the end, we have a much more complex stack with a lot of functionalities in terms of seed layers, in terms of pinning, crystallization. So that's important to mention. Of course, we have not to go with a thickness which is too large in terms of processing in order to integrate that. Well, on top of that, of course, even if the technology is complex, and we also saw yesterday in hard disk drives, the people did a lot of developments which allowed to this technology to emerge, and the big companies now are moving toward embedded MRAM production very soon, even if, of course, announcements were delayed in the recent period. So that's, I would say, the global picture. Now, why high speed and how the MRAM is related to this particular workshop. So just have a look to the memory hierarchy and what are the main needs for the future. If we look at the power consumption as a function of course, need of embedded electronics in the forthcoming years, with the different colors, we can see the switching power in green and yellow in the logic part, either the switching power or the leakage power, if it's a volatile memory. And in blue and light blue, the leakage power and the switching power in the memory. And we can see that in the future, there will be a big contribution coming from the power needed to write the memory in the logic part. What means the logic part? If we look at the memory hierarchy, which is actually dependence on the speed, density of different types of memories, of course, lower speed is on the bottom, higher speed on the top, lowest density on the top, highest density on the bottom. We can see that we have a continuous evaluation of types of memory. So we have the storage memory, which is not fast, but has to have a lot of density and capacity. And going up to the processor, what we can see is that we need very fast memory. And what is important with respect to what I said with this logic part is that we do not have too much, I would say, red color like this, which is depicting the non-volatile memory close to the processor or to the cache level. So in order to reduce, I would say, the power consumption in this part, we have to propose a non-volatile memory which is fast enough. And for the moment, there are no solutions except this MRAM. So there is actually, with the actual solutions, a speed mismatch in between the memory and the CPU, and the logic keeps awaiting data, and finally the logic issue is becoming a memory issue. Now the question is how to bring non-volatility close to the microprocessors, and for that we need a ultra-fast memory, typically sub-nanosecond, which is directly integrated in terms of process and design at the heart of the logic. So that's, I would say, one of the main market for the MRAM. And of course, if we are looking to the ultra fast, of course, going to the processor, we'd see what is really fast enough. So is the same type of diagram, but now in terms of density and speed represented differently. So how fast is fast enough? So typically, if we want to address the main memory in 100 megahertz, we can say that the actual perpendicular STT-MRAM can handle switching in the 3 to 20 nanoseconds. If we want to go in the cache, SRAM, register and processor, we have to go sub-nanosecond, and of course even faster for the processor. For that, we need a sub-nanosecond switching MRAM. So in the presentation today, I will give some ideas of the work we are doing in terms of what we call precessional switching, in terms of what we call the EasyCon STT-MRAM. I will not enter into the physics, but just some design aspects of the SOT indicating the advantages that this three-terminal device brings. And of course, people were mentioning about this SPICE project in which, of course, integrating a photonic and a spintronic chip together and doing an all-optical switching at very fast writing speeds could eventually, if we handle also the read speed, address much faster types of applications. So, this being said, so I was mentioning about the three concepts I will describe in the talk today to do fast switching. So the first one is what we call a precessional STT-MRAM with perpendicular polarizer. So as we saw in terms of memory cell, we have an STT, so spin transfer torque, in which we can write the memory with a given speed, and the question is how we can do it faster. So a classical STT-MRAM, in which if we look at the dependence of the spin polarized current with respect to the main terms which are entering inside, we can see that it is a vectorial product between the magnetization and the polarization. So typically, if we have a system either in plane or out of plane in which the reference and the storage layer are collinear, actually we have what we call an incubation time, which is needed in order to initiate the switching, and that incubation time is related to the thermal activation needed in order to initiate the reversal. So that means that in terms of reversal, we are discussing about what we call a stochastic reversal, having this incubation time preceding the thermal fluctuation, and typically that means that a reliable STT-MRAM writing would require more than few nanoseconds for writing. So the idea was to bring some non-collinearity to the system in order to get rid of this incubation time by adding what we called at that time a perpendicular polarizer. Of course, you can have a system in which you have the perpendicular STT memory and adding an in-plant polarizer. And by combining actually the two terms now, because now the free layer in the middle will fill two spin torques, one coming from the classical reference layer from the analyzer and one coming from the perpendicular polarizer. So we have two terms, one coming from the in-plane analyzer and the second term coming from the perpendicular polarizer. The first one is giving a bipolar switching, but of course with this incubation time, while the second one is giving what we call the out-of-plane oscillations, and this is, I would say, the working principle of what we call the nano spin torque oscillators. Now the question is how we can do something very fast, but also try to stop the precession of the magnetization at specific periods. In order to have this memory functionality. And for that, there are two aspects to address. One is what shape in order to have this bipolar switching, and eventually use of a transverse magnetic field, which is of course not very scalable, but at least from the proof of concept it can be helpful. So just some macrospin simulations indicating with these two contributions how the current density evolves with the pulse width, and typically if we do a cross section for an aspect ratio of 2 on this diagram, we can see that this out of plane precession of the free layer evolves with I would say a frequency which is in the gigahertz regime depending on the current density. So this is the basics of the spin torque oscillator. Modifying the aspect ratio, so increasing from 2 to 5 for the dimensions which are indicated here, we can see that this switching diagram is completely modified, and instead of having these alternating stripes of oscillations in opposite directions, we have non-oscillatory bipolar switching which can be achieved. So by going in this direction we have only one stripe, and typically we can achieve an ultra-fast reversal without an incubation time, which is typically less than the nanosecond. So that was on the simulation side. So we wanted to verify that. So this is just to indicate that typically is a quite complicated stack to be developed, processed, and in terms of real-time measurements, also quite challenging, done with Thibaut Devolder in Paris. And these electrical measurements are showing for the two aspect ratio. So we mimic what we did in the simulations, is that depending on the voltage we applied on the junction, we can have on the aspect ratio of 2 some oscillatory behavior, of course with the frequency increased when the voltage is increased, and we can extract the dependence of the frequency with respect to the current density, which actually indicate that the precession frequency depends linearly on the current density, and there are some dephasing of the precessional motion, of course related to the size of the cell, which is here 80 by 160 nanometer, indicating that maybe the inhomogeneous distribution of the magnetostatic stray field is creating some dephasing. Now, when we increase the aspect ratio to 5, we can see that we can obtain a single switching, not I would say oscillatory switching, and of course by increasing the voltage which is applied, we can do that switching in less than 500 picoseconds, the best results we obtained so far. Of course, by doing this, we have to apply on the tunnel barrier voltages which are approaching the volt range, which is in terms of reliability not very good, but just calculating some numbers with respect to the discussion yesterday of the energy needed to write a single memory cell, we can see that, for example, for this specific switching event, we have been able to do it with 90 femtojoule. So this aspect, large aspect ratio, allows for non-oscillatory fast and direct overwrite switching, and the precession stops at stable state after half a precession period. Of course, not having, I would say, an applied external magnetic field, as we don't know which is the initial direction, is a kind of toggling switching again. So every time you apply a switch, you will write in the opposite direction. So that's something I would say similar to issues we discussed with the all-optical switching. So the problem here for implementation for cache is that large cells would require large aspect ratio, and the question is if there is another way to obtain the desired bipolar switching dynamics, and of course adding a transverse magnetic field could help. I will not describe here, but typically is something that is useful. So that was what we call the precessional STT. Let me now describe the importance in terms of switching speed of what we call the second order anisotropy in perpendicular STT-MRAM. So these are just some images from the STT-MRAM we developed together with Leti, showing that, of course, we can obtain STT-MRAM based on interfacial perpendicular anisotropy with a specific switching diagram, voltage versus field, with well-defined frontiers in between the two states, so well characterized. So what we wanted to do is that typically in these easy axis measurements, in which we apply the field around the easy axis of the magnetization, we have an uncertainty on the switching mechanism, so which can be, depending on the size, either macrospin or can be also some nucleation propagation. And we have not much detail about the anisotropy itself. So what we did is we used on this type of junctions hard axis measurements to evaluate the anisotropy. And we did that for different dimensions, going down from 150 to 50 nanometer perpendicular pillars at different temperatures, going down to 5K. So while doing these hard axis measurements, actually we were able to model the RH curves only by introducing a second order anisotropy term, which depending on the temperature can have significant values with respect to the K1 factor. So now the question is how this K2, which indicate that the magnetization is typically oriented on an easy con, depending on, because we have a kind of reorientation of the magnetization due to this interfacial anisotropy when we vary the thickness. So what's the impact of this second order anisotropy on the switching itself? And let me just do a comparison in between. So these are simulated macrospin simulations with right pulse duration, which are 50 nanoseconds, and I will do after at 1 nanosecond. So for 50 nanoseconds, what we vary actually is just adding a second anisotropy term, which is either 0 or increasing slightly with respect to this K1. And what we saw in this switching diagram is that both the switching field and the critical current needed for switching are reduced when a second order anisotropy term is added. And typically when this ratio K2 over K1 increases, we reduce the delta factor. We see that the switching field is decreased, but we also have a voltage decrease. Now, what is important in this is a figure of merit, which is typically the critical current versus the retention factor. So typically, adding this second order anisotropy will degrade the retention, but can have a positive impact on the power consumption and also on the pulse duration. Typically, going from 50 to 1 nanosecond, we can see that this figure of merit is even larger at 1 nanosecond. So adding this second order anisotropy, which in principle, as we described with this non-collinearity, would provide again this initial angle which would trigger the magnetization reversal, is important for the fast switching. So I will not enter now into the detail of how to create this second order anisotropy, but we have results showing that typically, depending on materials which are in contact with the cobalt iron boron, the annealing conditions, we can tune the value of this second order anisotropy term. And finally, a third strategy for high speed is the SOT-MRAM. So SOT-MRAM, instead of using this spin orbit torque, instead of using the spin transfer torque, we're using a new effect, which is the spin orbit torque. And typically, we have a 3-terminal device. We are not passing anymore the current through the tunnel barrier, which is, I would say, positive from the endurance point of view. And there were recent results in the framework of a European project in between Spintec, Zurich, and Signalus, showing that we are able to go down to something like 100 picoseconds. Of course, this is obtained for relatively large values of the current in the bottom line, close to the, I would say, electromigration level. So for the moment, is not, there are material developments underway in order to reduce this current. The message I want to give here is that how to use this STT and SOT at the cache level. So you saw that memory hierarchy at the beginning. What we propose is to add at the different level of cache, L3 being the slowest cache level, L1 the fastest, some MRAM, to put some MRAM inside. So, and we did simulations using classical single-core processor, so cell level information extracting SPICE simulation, not from the project, but SPICE simulation. And the results are the following. And you can see here mainly the main parameters are in terms of area and energy consumption. when you do a combination of L1, which is the first term, and L2 and L3 is the second term. So doing a combination of SRAM plus STT or SRAM plus SOT, we reduce the area by 30% with respect to a classical SRAM, slightly lower for STT because of the cell itself, which is smaller than the SOT cell. What is striking is that even with actual values from the STT and SOT, we have a large energy consumption gain in that, about 60% reduction. So a best compromise for the SRAM, adding some magnetic memory at the L2 and L3 level, has very nice benefits. So just to summarize on these ultra-fast concepts, so I was showing that in order to go to this cache and above applications, we need sub-nanosecond switching MRAM architectures. I was discussing about different strategies we are starting, of course, each of them with advantages and disadvantages. The first one is what we call the precessional switching, in which we obtain the best results so far, 200 picoseconds, but in terms of reliability, not very good. Okay, something that is relatively reliable with 10 to the 5 cycles is 500 picoseconds, 90 femtojoule. We showed that using second-order anisotropy can help increasing the switching speed and reduce the stochasticity of the switching. The remaining challenge being to achieve a large thermostability factor together with this easy cone anisotropy. Of course, demonstration of this three-terminal SOT-MRAM in the lab. I was not describing too much experimental results, but showing that this has an impact on terms of area and power consumption in terms of L2 and L3 cache replacement. And remaining challenges are to determine, to have a deterministic switching without an external magnetic field. So far, there are some few demonstrations about doing this, but we have to couple this with reduced write current. I don't know how much time I still have.
It is practically over, but
it's
if
practically
you have one minute or so, do you need, how much do you need?
Okay, 1 minute. So these are just results from maybe from SPICE project, showing that with respect to the discussion yesterday, that even in the classical STT, heating can have a positive impact on the writing voltage. So even without doing the all optical switching. So that's an interesting aspect. And also with respect to the discussion yesterday, we have been able to do a kind of MTG stack with a terbium cobalt storage layer, which is not the best in terms of TMR, but we have been able to reach above 50% of TMR. So results are coming, studies are ongoing to do the switching of all optical switching of these layers. So I'll skip this part, which is how we handle the nanofabrication issues, the etching part, and what we call the perpendicular shape anisotropy to be stable below 5 nanometer, which actually modified our roadmap to the very high density. So I would like to thank all our collaborators working on the different aspects on MRAM, STT, all optical, perpendicular shape anisotropy, neuromorphic in spintec. You saw Bernard yesterday, so he's also contributing to this MRAM effort, and the people helping us with materials, nanofabrication, test, electron microscopy study, simulation, and theory. And I would like to thank you all for your attention.